Hi, we're the 101 Ballers, and this is our Stats 101B final project presentation. Cardiovascular disease is the #1 cause of death globally. If you had cardiovascular disease right now, would you like to know? If you answered yes to this question, then this presentation might be of interest to you. To make classifications, such as whether someone has cardiovascular disease based on certain medical predictors, we use complex algorithms, such as the random forest algorithm. When random forest makes classification decisions, we want to ensure that it has the highest possible accuracy, which can be measured by the metric of cross-validation accuracy. To determine which tuning parameters in the random forest algorithm are significant in determining its accuracy, we need to set up an experiment that allows us to see the effects the individual tuning parameters have on the accuracy. We can have a maximum of 35 runs in this experiment, and we want to compare two different designs, a 2 to the 7-2 fractional factorial and a 35-run optimal design. In order to compare these two designs, we need to assess how useful each of them will be in allowing us to interpret the results of the experiment. This can be done by comparing the correlations between the main effects and the two-factor interactions in each of the two designs.
Here are the pairwise correlation plots for the fractional factorial design versus the optimal design. As shown in Figure 1, the fractional factorial design can estimate all main effects without them being aliased with any other main effect or two-factor interaction. The fractional factorial design cannot estimate all of the two-factor interactions because some of the two-factor interactions are aliased with each other. As shown in Figure 2, the optimal design can estimate all the main effects and two-factor interactions with slight correlations to other main effects and two-factor interactions, but with no aliases. The fractional factorial design has multicollinearity between the aliased two-factor interactions, but no multicollinearity between the main effects and the two-factor interactions. On the other hand, the optimal design has some multicollinearity between almost all main effects and two-factor interactions, but no aliasing of any of the main effects or two-factor interactions. We recommend the fractional factorial design since it allows for the main effects to be estimated without any correlation to any other main effect or two-factor interaction. We created a data frame called Design by setting each of the 7 factors to either the high or low settings based on the 2 to the 7-2 fractional factorial design we chose. We use this design matrix as well as the predictor variables and responsive variables from the cardiovascular disease dataset as the parameters for the cross-validation RF function. The output of this function was the data we needed to analyze to determine the significant tuning parameters for the random forest algorithm.
The initial model we created to predict the accuracy of the random forest algorithm included all 7 main effects and all of their interactions. We used a half-normal probability plot to determine which of these main effects and two-factor interactions were significant. From this Daniell plot, class WT cut off the interaction of class WT and max nodes, and by extension, max nodes are significant factors in this model. This is a final model which only includes the identified factors from the Daniell plot. All of the factors we identified as significant were indeed significant in the regression model. To check whether this final model is valid, we need to look at the residual plots. From the residual plot, we can see that there's no pattern. This suggests that there is no major violation of the assumption of linearity or constant variance. From the normal QQ plot, we can see that the errors are very close to the line. This suggests that the errors are normally distributed. Overall, the assumptions are met and the model is adequate.
We think our design and model worked well for several reasons. Our design made use of the fact that fractional factorials of resolution 4 can give main effects that are unaliased and completely uncorrelated with any other main effect or two-factor interaction. This allowed the results from this design to be useful and easily interpreted. Also, the two-factor interaction that was in our model also was not aliased in any of our fractional factorial design. So the effect estimated in our model for that interaction was not correlated with any other two-factor interaction. Our model worked well because our residuals showed no sign of violating the assumption of constant variance or linearity, and the normal probability plot showed that the errors were approximately normally distributed. For future experimentation, we recommend that, if possible, a 64-run fractional factorial or full factorial design should be implemented in order to check whether any of the other interactions that were previously aliased in the 32-run design are significant. Thank you for watching.